Hello everyone, welcome to our presentation about robust online model adaptation by extended Kalman filter with exponential moving average filtering and a dynamic multi-epoch update strategy. I'm Abulikemu Abuduweili from Peking University. I was studying under Professor Changliu from the Robotics Institute, Carnegie Mellon University during this work. Supervised learning has widely used to obtain models to predict the behaviors of intelligent agents. Behavior prediction is a subtopic of time series prediction, which includes vehicle trajectory prediction during autonomous driving and human motion prediction during human-robot collaboration. The behavior prediction is to make inference on the future behavior of the target agent given the past and the current measurement of the target agent and its surrounding environment. The transition model for behavior prediction is yt equals f sigma x, where the input vector x denotes the stack of n-step current and the past measurement. The output vector y denotes the stack of m-step future behavior. Sigma denotes the parameter of the model. Although the trained model typically performs well on the training set, performance can drop significantly under slightly different data distribution. Just as this figure shown, this is a train set distribution and this is a task set distribution. For example, the table shows a performance comparison between train set and the task set. As can be seen, the MSE in train set is much lower than task set because of the different data distribution. For tasks without annotated corpora from the task domain, adaptation techniques are required to deal with the lack of domain-specific data. Online adaptation explores local overfitting to minimize the prediction error, which corresponds to a nonlinear least squares problem. Assume that the true model parameter changes slowly during adaptation. The process for online adaptation is summarized in algorithm 1. In adaptation, a predicted model observes instance sequentially over time. After every observation, the model outputs the prediction and receives grand truth. Then the online adaptation algorithm updates the parameter measured between the prediction and the grand truth. The goal of the adaptation is to improve the prediction accuracy in subsequent rounds. For prediction models encoded in neural network, most existing online adaptation approaches are based on stochastic gradient descent. However, these methods may be suboptimal in minimizing the local prediction error with slow convergence rate. Another solution is to use the recursive least square parameter adaptation algorithm, just as the figure. However, RLS can only adapt the last layer of the neural network, since it only applies to linear models. Our base algorithm is inspired by the recursive EKF method. The extended Kalman filter is one of the best methods for nonlinear parameter estimation, which is derived by linearizing the system equation at each time step and applying Kalman filter to the linear system. The EKF approach has been demonstrated to superior to the SGD-based approaches. By assuming that the grand truth changing very slowly, we can pose the parameter adaptation problem as a state estimation problem. We can apply EKF approach to adapt model parameter. In online adaptation, we assume that data in the distant past is no longer relevant to the current system. So, hence, we consider a weighted nonlinear recursive least square problem. The forgetting factor lambda prevents the EKF from saturation and increase the algorithm's ability to track a changing system. In addition to speed up the convergence of parameter estimation, we propose to apply exponential decade moving average for filtering the EKF optimization process. In SGD-based methods, numerous variants of EMA has been successfully used to speed up the convergence, including Polyek averaging and the momentum. By combining EKF and the forgetting factor, we propose a modified extended Kalman filtering with EMA techniques. The algorithm shows the modified extended Kalman filter with exponential moving averages. For the modified EKF-based approach, we can either apply EMA on the optimization step size V and apply EMA on the uncertainty matrix P. The lines 3 and 4 represent this EMA V, which is widely used in SGD-based optimization algorithms. It calculates the optimization step size V by decreasing the exponentially the older step size. The line 5 and 6 represents the EMA P. P is a matrix representation, the uncertainty in the parameter estimation. In order to attenuate instability during adaptation caused by anomaly data, we can smooth the inner state of the optimizer by pre-filtering P. In generic online adaptation, all data are equally considered. We run the adaptation algorithm chronically from the first data to the last data. Every data sample is used only once. Inspired by the curriculum learning, we introduced a more effective way to determine the adaptation epochs for every data samples during online adaptation. In curriculum learning, that said, it's particularly useful to differentiate easy samples from hard samples. In our dynamic multi-epoch update strategy, we define criteria C to determine the number of epochs, and we reuse the input-output pairs many times to adapt the parameter theta. Combined with our dynamic multi-epoch update strategy, we propose a very straightforward criteria C to determine the number of epochs for every sample, as shown in the algorithm. Two threshold, epsilon1 and epsilon2, is used to discriminate easy, hard, and anomaly samples. Before updating the parameter, we calculate the prediction error of the sample. Then if the error satisfies less than epsilon1, we run single epoch update for the easy sample. If the error satisfies the error greater than epsilon1 but less than epsilon2, the sample is considered as the hard samples. Then we reuse the sample and run the adaptation twice. The rationale is that for a hard sample, an adaptation optimizer may not learn enough under single epoch parameter update strategy. If the error satisfies greater than epsilon2, the sample is considered as an anomaly sample. Then we skip the parameter update process. The rationale is that if the cost is too high, the sample is likely to be an anomaly point in the data distribution, which may destabilize the model adaptation process if learned. By combining all extensions with the EKF-based algorithm, we introduced the robust online adaptation algorithms, MEKF with EMA and DME. In the experiment, we consider a multitask prediction problem for simultaneous intention and trajectory prediction. The figure illustrates this online adaptation framework, which only adapts the last layer of the encoder parameter. In online adaptation of multitask learning, the adaptation algorithm updates its prediction model, only consider the prediction trajectory and measured trajectory. The grantor's intention is not available for the online adaptation since it's not directly observable. We construct the RN-based encoder-decoder classifier structure in our experiment for simultaneous intention and trajectory prediction, as shown in the figure. Trajectory prediction is based on encoder-decoder structure, and intention prediction is based on encoder and classifier structure. Both the encoder and the decoder are composed of single GRU, and the classifier is composed of two-layer FC neural network. In order to improve the performance of a line training model, an attention layer is applied to the output vectors of the encoder. We used mocap dataset, that's for human motion capture dataset, and NGSIM dataset, that's the benchmark dataset for autonomous driving in our experiment. In experiment of adaptation, we studied the performance of various adaptation algorithms on hidden weights of encoder offsets of line trained models. Table 1 shows the prediction performance of online adapted models using different optimizers on the mocap dataset and the ngsim dataset. Compared to stochastic gradient-based algorithms, the EKF-based algorithms perform better. In addition, the MEKF with EMA and the DME has the best performance among all due to the extensions inspired by exponential moving average filtering and the dynamic multi-epoch update strategy. The variance of performance using different optimizers on the ngsim dataset is shown in the parentheses. In particular, the standard deviation of the prediction accuracy, as well as the standard deviation of the prediction trajectory are shown. For trajectory prediction, for EKF-based approaches have lower standard deviation than the SGD-based optimizers. We studied the effectiveness of the proposed extensions to MEKF. The results are shown in table 2. EMAV, or momentum, barely improves the performance. Two potential reasons are, firstly, the momentum does not have EKF-based optimizers. Why? The optimization step size of EKF-based approach is already closer to optimum than that of SGD. Second, the moving average on the parameter of the step size is more applicable to offline training than to online adaptation. The inapplicability is due to the fact that online adaptation can only process data sequentially in time, which is significantly different from the shuffled, repetitive, and the batched process in offline training. EMAP slightly improves the performance of MEKF. Filtering of uncertainty matrix P can smooth the inner state and improve convergence. Dynamic multi-epoch update strategy improves the performance of MEKF, and it has the best performance among all the proposed extensions. Let's show the demo for hand trajectory prediction with our online adaptation algorithm. The dark blue points represents next 10 steps prediction. The light blue points represents next 10 steps to feature points. As can be seen, the predicted results are very close to the true points. This is a demo for multitask prediction problem with our online adaptation algorithm during human-robot collaboration. The model predicts the trajectory and the intention of hand simultaneously. Then the robot arm reacts to the intentions. The blue points represent the next 10-step predictions. The predicted intentions and related probability are as shown in upper left of the screen. This work studies online adaptation of neural network-based prediction models for behavior prediction. In order to improve the performance and the convergence of EKF-based adaptation algorithm, exponential moving average filtering was investigated. Then this paper introduced a dynamic multi-epoch update strategy, which is compatible with any optimizer. By combining all extensions with the base MEKF algorithm, we introduced the robust online adaptation algorithm MEKF with DMA and the DME. In our experiments, we demonstrated the effectiveness of the proposed adaptation algorithms. Thank you for your attention. If you have any questions, please don't hesitate to ask us.